So we're going to be working on Chapter 8, Lesson 2, Dividing Monomials. So what we're going to learn in this lesson is how to simplify expressions involving quotient of monomials, how to simplify expressions containing negative exponents. Some vocabulary to keep in mind is what is a zero exponent and what is a negative exponent. So how can we compare pH levels? So to test whether a solution is a base or an acid, chemists use a pH test. This test measures the concentration C of hydrogen ions in moles per liter in the solution. And so it's represented by this equation, C equals 1/10 to the power of pH. The table gives examples of solutions with various pH levels. You can find the quotient of powers and use negative exponents to compare the measures of the pH scale. So here's an example here. So, quotients of monomials. In the following examples, the definition of a power is used to find quotients of powers. Look for a pattern in the exponents. So if I have 4 to the fifth power over 4 to the third power, right, that's a quotient because I'm dividing 4 to the fifth power by 4 to the third power, right? If I write it in expanded form, 4 to the fifth power is 4 times 4 times 4 times 4, right? 4 times itself 5 times, I mean. And then 4 to the third power is 4 times 4 times 4. Well, if you remember, people's favorite thing to do is to cancel things out, right? If you divide 4 divided by 4, those cancel out and really just give you 1, right? So this would cancel out this one cancels out this one cancels out this one. And really, these 5 factors on top and these 3 factors on the bottom, well, these would cancel each other out. And it leaves me with 2 factors, right? 2 factors of 4, 4 times 4, which is 4 squared, right? And if you can see, how do I get from 4 to the fifth power divided by 4 to the third power all the way to 4 squared is really what I was able to do was subtract the exponents, right? 5 minus 3, right? The exponents, if I do 5 minus 3, would give me 2. Let's take a look at another example here. What if I had 3 to the sixth power divided by 3 squared? Again, if I wrote it out in expanded form, 3 times itself 6 times, divided by 3 times itself 2 times, again, these 2 up here will cancel out these 2 3's down here, right? These 2 factors of 3 cancel out these 2 factors of 3. So really, it's 6 minus 2, which would leave me with 4 factors of 3, which is 3 to the fourth power. Again, looking for that pattern that you can see that if I have the same base, I can subtract their exponents when I'm dividing. Very similar to the product of powers rule where when I was multiplying two things with the same base, I would add their exponents. Well, now with dividing, I'm going to be subtracting their exponents. So these and other examples suggest the following property for dividing powers. All right, this would lead us to our quotient of powers rule. To divide two powers that have the same base, subtract the exponents. So again, here they give you an example. If I had b to the 15th power over b to the 7th power, right? That's when I'm dividing these two things, I can subtract their exponents because they have the same base. And 15 minus 7 would give me 8. So I would have b to the 8th power. So let's look at this first example here of something you're going to be asked to do. Quotient of powers. Simplify a to the 5th power times b to the 8th, all divided by a b to the 3rd power. Assume that a and b are not equal to 0. So assume that a and b are some number that's not 0. So again, I'm going to write this out. So a to the 5th power over a, I can kind of group these using the same base. B to the 8th power over b to the 3rd power. So here I would just rewrote it so that way I have the same things over each other, right? So a to the 5th power, and remember that's a to the 1st power. So again, same base, I'm going to be able to subtract their exponents. And same thing over here, b to the 8th over b to the 3rd, same base. And I can go ahead and subtract the exponents, right? Use that quotient of powers rule. So 5 minus 1 and 8 minus 3. So that's going to leave me with a to the 4th power and b to the 5th power. So that's how I'd use my quotient of powers rule to be able to simplify this expression. In the following example, the definition of a power is used to compute the power of a quotient. Look for a pattern in the exponents. So here I have 2 to the fifth power, or sorry, 2 over 5 all to the third power, right? So one way to look at it is you can write it out, right? So 2 fifths to the third power means 2 fifths times itself 3 times. So 2 fifths times 2 fifths times 2 fifths, right? 3 factors of it. And then I can go ahead and just rewrite it, right? Using the associative property, right? All these things are just being multiplied together, right? I'd multiply all the stuff across the top, the numerator, and all the stuff across the bottom, the denominator. So 2 times 2 times 2 times 2 is 2 to the third power. And 5 times 5 times 5 is 5 to the third power. So it would leave me with 2 to the third power over 5 to the third power. This and other similar examples will suggest the following property: the power of a quotient. So to find the power of a quotient, find the power of the numerator and the power of the denominator. And basically, one way that I like to think about this is whenever you have a fraction with an exponent, really it's like applying that exponent to the numerator and applying that exponent to the denominator, right? So notice how if I have c over d all to the fifth power, then that's c to the fifth power over d to the fifth power. That is the power of quotient rule. So let's take a look and apply this in an example. So here it's asking us to simplify 2p squared over 3 all to the fourth power. So same thing, I'm going to go ahead and start by simplifying this by applying this exponent to the numerator and applying this exponent to the denominator. So 2p squared is to the fourth power and 3 is to the fourth power. And then I'm going to continue to simplify this, right? If I apply this exponent, right, this fourth power to everything in here, that's going to be 2 to the fourth power and p squared to the fourth power. Well, now we can continue to simplify this. 2 to the fourth power can be simplified. I can do 2 times itself 4 times, which is 16. P squared to the fourth power, that's a power to power, so I can multiply those exponents, and that gives me p to the eighth power. And then obviously 3 to the fourth power can be simplified to 81. 3 times itself 4 times is 81, right? 3 times 3 times 3 times 3 is equal to 81. So that's how I'd use the power of quotient rule. So next we're going to talk about zero exponents and negative exponents. So this is probably something you haven't had a lot of experience with. Using a calculator will usually give you the answer using exponents, but it's really easy to kind of take a look at it if we understand basic exponents. So let's start with something we already know. So if I asked you to calculate what is 2 to the second power, right, 2 squared, you would tell me, well, that's 2 times 2, which equals 4. And if I were to take it another level and ask you, well, what's 2 to the third power? Well, you would say, well, 2 times 2 times 2, 2 times itself 3 times, that's 8. If I were to ask you for 2 to the fourth power, similar strategy, right? 2 times itself 4 times, which equals 16. If I ask you for 2 to the fifth power, you would say, okay, 2 times itself 5 times, that's going to give me 32. And if you notice a pattern here, all I'm doing each time is just multiplying by 2 an extra time. So really 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And if I were to go one more step and say 2 to the sixth power, really that's just 32 times 2, which is 64. So very easy to see the pattern that I'm just doubling each time, right? I'm just multiplying by 2 an extra time I go up, right? So if I were to ask you to go backwards, instead of multiplying by 2, can we just divide by 2? What's 64 divided by 2? That's 32. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. So we can kind of see this pattern. As we go up, we're multiplying by 2, and as we go down, we're dividing by 2. So if I were to ask you to say, hey, what's 2 to the first power? That's probably pretty easy. 2 to the first power is just going to give me 2. And it makes sense because 4 divided by 2 is 2. So if we can acknowledge that this pattern exists, we can continue to follow that pattern into zero and negative exponents. So if I were to ask you to continue to divide by 2, you could follow this pattern. 8 divided by 2 is 4. 4 divided by 2 is 2. And what's 2 divided by 2? 2 divided by 2 is 1. So if I asked you, well, what's 2 to the 0 power? That's 1. Many people will try to tell me that 2 to the 0 power is 0, but it's not. And you can tell by the pattern that it has to be equal to 1, right? Let's continue this pattern. What's 1 divided by 2? 1 divided by 2 is a half. So if I were to continue to follow the pattern on this side, 2 to the negative first power, right? It's just going down by 1. So going down by 1 from 0 would be negative 1. So 2 to the negative first power has to be equal to 1/2, right? Because I'm just continuing to divide by 2 as I go down. So 2 to the negative 2 power, again, 1/2 divided by 2 is 1/4. 2 to the negative third power is 1/8. 2 to the negative fourth power is 1/16. So you start to recognize this pattern that these negative exponents of 2 are actually just fractions, right? 1/2, 1/4, 1/8, 1/16. So one other thing I wanted you to take a look at that's a really important pattern to recognize is if I were to ask you to look at 2 to the second power and 2 to the negative second power, what do you notice about its two answers, right? 2 to the second power is 4. 2 to the negative second power is 1/4. Do you notice that the two answers are reciprocals of each other, right? They are just upside down fractions of each other, right? So this is like 4 over 1, that's 1 over 4. So really negative exponents are reciprocals of each other, right? Let's look at another one. What about 2 to the first power and 2 to the negative first power? Notice how the one is when the exponent is 1, the answer is 2. When the exponent is negative 1, it's 1/2, right? They are reciprocals of each other. Let's look at another one. What about 2 to the third power and 2 to the negative third power? Again, reciprocals of each other. 8 and 1/8. Let's look at one last one. 2 to the fourth power. 2 to the fourth power is 16. 2 to the negative fourth power is 1/16. Again, recognizing that those are just reciprocals of each other. Okay. So, really, when we're dealing with positive and negative exponents, we can understand that they're just reciprocals of each other. So, if I know what 2 to the fourth is, 2 to the negative fourth is really easy because it's just the reciprocal of that, right? It's just that same fraction, but the numerator and the denominator are switching places. All right. So, understanding these patterns in zero and negative exponents, it allows us to examine them a little bit more understanding. But let's take a look at it in a slightly different way. If I had 2 to the fourth power over 2 to the fourth power, right? The same base, I can use my quotient of powers, right? So I would subtract their exponents, right? So 2 to the fourth power over 2 to the fourth power, well, I'm just going to do 4 minus 4. Well, I know 4 minus 4 is 0. So that's going to give me 2 to the fourth power, right? We can also look at this using a secondary method. Again, 2 to the fourth power or 2 to the fourth power. If I were to write these out, right, times itself 4 times over 2 times itself 4 times, these all cancel each other, right? Really, they would all cancel out, and it just leaves me with 1 over 1, which is equal to 1. So here, using these two different methods, I can show you that clearly the same problem giving me the answer of 2 to the 0 power and the other one giving me 1, these have to be equal to each other, right? And another way to think about it, to prove to you that 2 to the 0 power actually equals 1, is if you ever divide, right? So 2 to the fourth power, 2 to the fourth power, right? Gives me 16, right? 2 to the fourth power, 2 times itself, 4 times is 16. So 16 divided by 16 is always equal to 1, right? Whenever you divide something by itself, it always gives you an answer of 1. Again, further proof that 2 to the 0 power is equal to 1. So lots of different ways to prove that 2 to the 0 power is equal to 1. So since um, this leads us to our kind of key concept here is when we're talking about a zero exponent, and this is anything to the 0 power, right? Any non-zero number raised to the 0 power is always going to be equal to 1. Okay? So if I have a to the 0 power, that's always going to be equal to 1. Okay? As long as that number isn't 0, as long as a isn't 0, right? 0 to the 0 power doesn't really work. But negative 0.25 to the 0 power is equal to 1. Anything, whether it's a decimal or a fraction, anything to the 0 power will always equal 1. Okay. Many people will want to tell me it's equal to 0, but based off all the stuff we've examined, it's equal to 1. So let's see if we can use this 0 exponent to help us simplify a problem. So let's look at A here. So A says negative 3x to the fifth y over 8xy to the seventh, all to the 0 power. So some people might look at that and say, whoa, that looks really complicated. But look, everything inside is raised to the 0 power. And based off the rule we just talked about, anything to the 0 power will always be equal to 1, right? So regardless of what is being taken to the 0 power, it's always going to be equal to 1 because anything to the 0 power is 1. So that first one was a pretty easy one. Let's take a look at this second one here. So again, t to the third power, s to the 0 power over t. Well, really, I can see that s to the 0 power, I can simplify that, right? S to the 0 power is going to be equal to 1 because anything to the 0 power is 1. So t to the third power times 1, well, that's just going to be t to the third power. And now I can use my quotient of powers rule, right? T to the third power over t to the first power. Again, subtract their exponents. So 3 minus 1 is 2. So that's going to leave me with t squared. So again, these are just a couple of ways that you can use the property of the 0 exponent to help you simplify an expression. So let's investigate negative exponents in a slightly different way. We can simplify these expressions like a squared over a to the fifth in two different ways. So again, using our quotient of powers rule, right? I have a squared over a to the fifth. So again, if I use the quotient of powers rule, that would be subtracting their exponents. And again, you always subtract from the top, right? So it would be 2 minus 5. So 2 minus 5 is going to give me negative 3. So 8 to the negative 3 power, right? And remember, we talked about negative exponents and what they mean. And really, they mean reciprocals of each other, right? So if I examine it using this second method, this will kind of show us exactly what we mean. So if I have a squared, that's 8 times itself twice, right? 8 to the fifth is 8 times itself 5 times. And again, if we do our canceling technique, this would leave us with 1 over 8 to the third power, right? Because you're only left with 3 factors of 8 on the denominator, the bottom of the fraction. So 1 over 8 to the third. So this would tell us that 8 to the negative third power has to be equal to its reciprocal, which is 1 over 8 to the third, right? We can see that they are it's the same fraction, but upside down. So clearly these two have to mean the same thing. So again, if I know 8 to the third power, I can find 8 to the negative third power, right? So again, whenever you're dealing with negative exponents, all you're dealing with is reciprocals, okay? So anytime you have a negative exponent, all you have to do is change its location in a fraction. So if it is in the numerator, you can move it to the denominator, or if it's in the denominator, you can move it to the numerator. So if I have 5 to the negative second power, that would be the same as 1 over 5 to the positive second power, or 1/25th, right? It's reciprocal. Or if I have 1 over m to the negative third power, so this is an example where you have one in the denominator, you can move it up to the top, to the numerator, which would just leave you with m to the third, okay? These are equivalent to each other. So whenever you're thinking about negative exponents, think about reciprocals, right? Think about changing its location of where it is in the fraction. So, an expression involving exponents is not considered simplified if the expression contains any negative exponents. So, whenever we're dealing with simplifying expressions, we want to make sure that we deal with negative exponents and turn them all into positive exponents. And again, how do you do that? By converting it to its reciprocal. So, let's go ahead and work on this problem here. So, I have b to the negative third power, c to the second power, over d to the negative fifth power. So here I can see that I have two negative exponents. So again, remembering that b to the negative third power is just equal to 1 over b to the third power, I know that this can go down to the bottom to become a positive exponent. And d to the negative fifth power, again, to deal with it, I have to move it to the top of the fraction into the numerator to make it a positive exponent. So here we can deal with it. Here I'm just going to write it out as separate fractions. So b to the negative third power is on top over 1, c squared over 1, and d to the negative fifth, right? So 1 over d to the negative fifth. So really, I just rewrote this whole expression as 3 separate fractions so I could look at each individual one separately. So again, b to the negative third power, think of it as its reciprocal. Just go ahead and flip it upside down, and it becomes a positive exponent. C to the second power over 1, we want to keep that the same because we want to keep that a positive exponent. And d to the negative fifth power, right, we're going to go ahead and do its reciprocal and flip it to the top. So d to the positive fifth power. So again, remembering that negative exponents just represent its reciprocal, right? Just change the location of where it is in the fraction. So now I can go ahead and just multiply these back out. If I multiply these back out, 1 times c squared times d to the fifth gives me c squared d to the fifth. And b to the third times 1 is just b to the third. So I was able to convert all of these negative exponents into positive exponents now. And there's nothing left, nothing has the same base, so there's no exponent rules I can continue to apply. This is as simplified as it gets. Let's look at a second one here. Here I have negative 3 a to the negative fourth, b to the seventh, 21a squared, b to the seventh, c to the negative fifth. So again, I'm going to go ahead and try to simplify this using my exponent rules. So I'm going to rewrite this again as separate fractions, and I'm going to group things that have the same base. So negative 3 over 21, I'm going to group those together because those are just numbers. A to the negative fourth over a squared, those have the same base, so I group those together. B to the seventh over b to the seventh, again, same base, I'm going to group those together. And then c to the negative fifth doesn't have anything to group with, so I'll just make it 1 over c to the negative fifth. So again, I just rewrote this as separate fractions so I can focus in on each one separately. So negative 3 over 21, that is just a simple fraction that I can simplify, right? Both 3 and 21 are divisible by 3, right? So that can be simplified to negative 1/7. A to the negative fourth over a to the second, right? So again, quotient of powers rule, right? So just subtract their exponents, negative 4 minus 2. Again, here, same base, subtract their exponents, 7 minus 7, which is going to give me b to the 0. And here, again, we can just move, we can do the reciprocal, right? So we're going to move this to the top of the fraction to make it a positive exponent. So it's just going to be c to the fifth. And then I'm going to go ahead and write this as negative 1/7, or 1 over 7. A to the negative sixth, b to the 0, c to the fifth. So again, if I wanted to continue to simplify this, right, I can deal with this negative exponent. Instead of being in the top, it would move to the bottom of the fraction. B to the 0 power, that's just the 0 exponent rule, right? Anything to the 0 power is going to be 1. So b to the 0 power just becomes a 1. So times 1. And so when I simplify this, this is what it's going to look like. And again, I'm just going to go ahead and multiply this all across, right? And it's going to leave me with negative c to the fifth, right? Because that goes on top. And then 7a to the sixth in the denominator on the bottom, right? When you multiply this all out, this is the simplified answer that you get. All right, thank you guys for watching. Let me know if you guys have any questions.